In this video, we are going to finish up our work on Chapter 8, Section 1, looking at simplifying and estimating square roots. So in the standards, we're going to be focusing on 8th grade. Those of you guys who are teaching 8th grade will most likely have students who are on grade level and they're in that pre-algebra class. And at the same time, you'll have an advanced class or two, depending on the team, where your students are in Algebra 1. So you're going to need to be very familiar with both the 8th grade pre-algebra standards and the Algebra 1 standards. In 8th grade, we're estimating and comparing the value of irrational numbers. And our irrational numbers in 8th grade, we have the number pi, which we're looking at in our geometry unit. And we also have numbers like square root of 7 or square root of 20, not perfect square numbers that are inside of a square root. And we're going to plot them on a number line. So this may be a little bit different than the plotting that you're used to, because irrational numbers we cannot put exactly in the right place because they never end. Rational numbers we can put exactly in a specific place. If we need to, we can change them to a fraction so we know how to split up that number line, but irrational numbers do not change into fractions, and so we cannot do that. In Algebra 1, we're simplifying our radicals. So I'm going to show you guys the way I did both of these when I used to teach 8th grade. So for simplifying square roots, what I found to be the easiest was to go from factor trees. There are many methods of simplifying square roots. The perfect square method is one that's very popular. I personally did not choose to do the square root method I did not choose to do the perfect square method with my students because I found that most of them didn't know their perfect squares. So trying to figure out the perfect square number that divides into the number that I had turned out to be very counterproductive. It was much easier to do factor trees because they've already been practicing prime numbers in previous grades. So for 45, let's do a factor tree there. 45 can be divided 9 and 5. 9 is not a perfect square number, so let's do 3 and 3. And then one thing that I found to be really helpful at this point, if I cross out my composite numbers, that is going to help us to keep ourselves organized with what we need to do. So square. Think about the idea of square. 3 squared or 7 squared, that means multiply the number by itself. So 3 squared is 3 times 3, 7 squared, 7 times 7, but it's important that there are always 2. So when you do square root, which is the inverse of square, it undoes the squaring. You're going to need 2 numbers just like you do for squaring. So I'm going to circle everything that I have a pair of. In this case, I have a pair of 3s. Now, the way I described it to my students is it's sort of like when you go swimming at summer camp. You have to have a buddy to go outside and get in the water. If you don't have a buddy, you don't get to go swimming. So 3 has a buddy. 3 gets to come outside, but 5, poor 5, he does not have a buddy. He has to stay inside the house. So that's the way I help them keep their thoughts organized. So squaring and square root are inverses of one another, and that's why I always need 2. Now at my level in 11th grade, we're also doing cube roots and fourth roots, so I have to have different numbers of numbers in my circle. But you guys in 8th grade with your Algebra 1 students, you're only going to focus on square roots, and so you're going to have 2 numbers inside the circle. Okay, let's do the same thing with 180. So 180, that's 18 times 10. Using my divisibility rules there, I see it ends in a 0, so 10 is the easiest choice for me there. 18 is 2 times 9, and 9 is 3 times 3. 10, 2 times 5. And then just like I did before, I'm going to go scratch out all my composite numbers. And the reason why is because if I'm going to tell my students that all the numbers that are left, all the numbers that don't have a buddy, have to go back inside, well, 18, 10, 9, those don't have a buddy. And so sometimes my students will accidentally use those numbers and put them back in the house, even though they've already simplified and factored those further down. Okay, now square root and square are opposites. Square means 2, number times itself. So I am going to circle the pairs. And it doesn't matter if the pairs come off of 2 different branches of the tree. Anytime I have pair anywhere in the factor tree, I can circle it. And the one, again, who doesn't have a buddy, poor 5, he has to stay inside. Now, the numbers that I have circled, when I bring them outside, I have to multiply them together. So I have one circle of 2's and I have one circle of 3's. 2 times 3 is 6. So my simplified form of the square root of 180 is 6 square root of 5. Okay, let's try square root of 60. Let's see what happens there. So again, I'm going to use my divisibility rules, and I see that 0, so I'm going to do 6 times 10. Neither of those is prime, so I'll keep dividing. All right, and then I'm going to cross out my composites because I want to keep my thoughts organized. Okay, squared and square root are opposites. That means I need two numbers. I see two 2's right there. So I knew 2 comes outside. Now before, when we had the 2 and the 3 both circled, we multiplied them together to put them on the outside. We're going to do a similar thing here. 3 and 5 are both not circled, so I'm going to multiply them back together and put them on the inside. All right, let's do 200. I see two zeros, so I'm going to use 100. And I know 100 is 10 times 10. Okay, now remember you guys, I told you need two numbers to come outside the square root. At this point, you could circle your 10 and your 10. I would probably not choose to do it that way with my class, only because 10 and 10 are not prime, and it confuses people. I like to do it every time the same way as much as possible so that it eliminates confusion. But if you have students who are a little bit more advanced and who can handle that, it's totally fine for them to circle the 10 and the 10 at that point and not go down to the 2 and the 5. Because when I circle to come outside, you can see I've got a circle of 2's. Whoops, I missed my 2. And I've got a circle of 5's. And 2 times 5 on the outside, that's 10, which is the same thing I would have gotten before. And then I have this 2. It doesn't have a buddy, so it has to stay inside. So square root of 200 simplifies to be 10 square root of 2. Now, once you get up to Algebra 2, we have all sorts of applications that we do with square roots. In Algebra 1, mostly you just simplify them. You do a little bit with them in the quadratic formula, but mostly you're just going to be simplifying with them. In geometry, you're going to do a lot of stuff with those as well as you work with the Pythagorean theorem. And you do a little bit with the Pythagorean theorem in 8th grade, so that would be helpful there as well. Okay, so let's look at estimating square roots. This is more of a pre-algebra skill, a grade level 8th grade skill. So to do my estimation, I need to figure what is the perfect square number that is closest to 25. Well, it turns out 25 is a perfect square number. So I would start off with some of these with your students and say the square root of 25 is 5. And then we're going to put that on our number line down here. And there's the square root of 25 right there. The square root of 25 is exactly equal to 5. It is not an irrational number, so I can put it exactly where it needs to be. And I would practice that with several. Square root of 4 is exactly 2, so it's going to go here. Because you're going to need them to be familiar with the perfect square numbers in order to get into what you need them to do. Now that's different than the idea of using perfect square numbers up here, because what happens in these sorts of problems is you're supposed to be able to recognize that 60 is 4 times 15. Well, most people didn't memorize their times tables up that far, even though 4 is a perfect square number they're familiar with. And so it turns out that this perfect square method on this one is not as beneficial as maybe some other things. On the other hand, with this, I just need to recognize that 25 is a perfect square number or 4 is a perfect square number. So let's put that to use with an irrational number, like square root of 22. There's nothing I can do to simplify square root of 22. It's 2 times 11, so I can't even bring anything outside of the square root symbol. And what I want to do with my 8th graders is give them the number sense of where square root of 2 is on the number line. So what we're going to do is we're going to find the perfect square number that is larger than that one and also smaller than that one. So if they need to go through in their mind, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, that's totally fine. It's going to help them become familiar with those numbers and help them get to the place where they need to be. Eventually, they're going to figure out that the square root of 22 is in between the square root of 25 and the square root of 16. Those are the perfect square numbers on either side. Square root of 25 is 5. Square root of 16 is 4. So if I put some numbers on my number line down here, I know that the square root of 22 is going to be in between 4 and 5 because the square root of 22 is in between the square root of 16 and the square root of 25. Okay, so let's see. The distance between 22 and 25 is 3. The distance between 16 and 22 is 6. So the square root of 22 is going to be closer to square root of 25 than it is the square root of 16. So I'm going to put it here, more than halfway past, and that's going to be the square root of 22. So if I had to estimate that, and when we did our end of grade testing in 8th grade, this was the type of question that was on there, and you would have to estimate what that square root would be. Well, I know that the square root of 16 is just plain 4. The square root of 25 is just plain 5. So 22 is going to be 4 point something. It's not right in the middle. It's not 4.5. It's closer to 25. So let's estimate it at 4.7. And since this, at least the one that we took, I'm sure it has changed since then, but the one that we took was a multiple choice test, and you just had to pick the best answer. And 4.7, even if the answer was 4.8, 4.7 is going to be your best guess, and they're not going to have something so close that you can't tell the difference. The other choices are probably going to be like 4.2, 4.4, maybe even 5.1. And so 4.7 is going to be your best guess on that. All right, let's do another one. Square root of 40. Okay, so our first job is to figure out which perfect square numbers are on either side of 40. Well, slightly smaller than 40, I have the square root of 36, and slightly larger than 40, I have the square root of 49. So I know the square root of 49 is 7. I know the square root of 36 is 6. So if I put those on my number line, I know that the square root of 40 is going to be somewhere here in between 6 and 7. Okay, so let's see if we can get a better estimation. From 40 to 49 is 9 units. From 36 to 40 is only 4 units. So I know that square root of 40 is going to be closer to square root of 36 than square root of 49, which means it's going to be down here closer to 6 than to 7. So if I had to estimate, 4.5 is going to be too big. I'm sorry, not 4.5, 6.5 is going to be too big. So I'm going to maybe guess 6.3. That is smaller than 6.5. It's putting me closer to 6 than to 7. And again, if it's a multiple choice test, I just need a good guess. I need something that's close. And 6.3 is going to end up being a good guess.